live transmission is
Oh,
starting.
actually. Oh no, now it's going live right now. So I guess
Okay.
So I guess I have to present you Sandra again. Sorry about that. Connection problems.
Live
So,
transmission
well,
is
yes. See. I think we are now live. Sorry about that. So welcome everyone to lawphysics webinar. My name is Alejandro and I'll be today's host. Today we have the pleasure to have Sander Mooij, and he's going to talk about renormalisation, finite renormalisation, and naturalness. He did his PhD at the University of Amsterdam, and then he moved to Santiago de Chile for a postdoc, and then to another postdoc at Lausanne, Switzerland. He's an expert in perturbative QFT, the intersection between cosmology and particle physics. We're very happy to have you today. So remember that you can ask questions over YouTube, Twitter, or email us the questions, and then they will be read at the end of the transmission. So thank you, Sander, and take it away.
Thank you. So I told you 2 minutes ago that I'm very honored with the invitation. I still stand with that statement. Let me see. So I share my screen. Let me see. Wait, now my computer has to think about this, because now I think you can. I think now you have the whole thing.
Perfect.
Right?
Yeah, we can see your screen.
Okay.
Thank you.
Yes. So good. So yeah, I wanted to talk about this this work that I did with my boss in IPFL, Misha Shaposhnikov. Well, we've been working on it for quite some time. Now, well, I think it's very nice. Other people, like referees, think it's either wrong or trivial. So, well, I'm very curious for your opinion. But now I see that Alejandro froze in my screen. So, are you still with me?
Yes, it's right. Yes.
Okay, good. So, let me tell you, the whole aim of the talk is to challenge the standard naturalness picture, and I will explain exactly what I mean by that. And to that end, well, first we will review that, then I'll show you what I want to say. And then we're going to talk about the standard way to do renormalization with all the intermediate infinities. And then I'll show you another way to do it without infinities or large corrections. And with that, well, I hope to convince you that naturalness is not a good guiding line in physics. So let me see. Let us begin just from the standard model. Here it is. It has been around for 30 years already, at least. And the question is, will there be something else? So probably the standard model is valid until some energy scale lambda. And at that energy scale, we expect new physics to show up. The question is, what is the value of lambda? We have, well, there is the proposal of supersymmetry and composite Hex models, large extra dimensions, and then you will typically see that this scale of new physics is around 1000 GeV. It could be, well, it could be that new physics coming up much later in the theory of grand unification. Typical scale is 10 to the 16. Quantum gravity will happen around the Planck scale, 10 to the 18. Perhaps there's no new physics at all. Then lambda is, well, goes up to infinity. The point with lambda is that apparently the fact that there is new physics, that there is this very high scale in the game, also changes low energy physics. So here you see just a cartoon of how you would compute the Higgs mass. There is the standard tree-level contribution, and then there's a loop. And if in this loop there's a particle running, which is like a new part of the extension of the standard model, which comes into play at this large scale lambda, then this will be a very large contribution to the mass, which means that when you renormalize, you will need a very large counter term to cancel that and to still end up with the mass of the scale of that you observe, which will still end up with 125 GeV. So the larger lambda, the larger the cancellation you need between heavy loop and counterterm. And in general, so that's why I say unnaturalness, this unnatural cancellation grows with increasing lambda. What about lambda? Well, there could be that there's supersymmetry, and if supersymmetry would be unbroken, then every loop, the effect of every loop, is cancelled by a loop with the corresponding sparticle, like superpiner of the particle in the original loop, and that would be, well, then there would be no fine tuning at all. Now, by now we know that unbroken supersymmetry doesn't exist. It could still be broken at TeV scale, and then the cancellation that we need will be of order TeV. So that's still relatively small. So in general, this general statement is that any new physics or any new TeV physics lowers lambda and therefore improves the naturalness of the theory. And that is why people are very interested in these TeV physics models, because then it will make our world more natural. Just because the cancellations we have in the computation of mass, for example, of the mass of the Higgs field, these cancellations become much milder if there is low energy physics, and that's why there's a big hunt for TeV physics guided by this line. So that's a standard naturalness picture. And now in the rest of the talk we want to challenge that. So I want to talk about standard renormalization. So again, now I will tell you what our answer is to this. So first, I just give you a small overview of the talk. As I say, the aim is to show the absence of meaning in UV divergences and also in the cancellation of large quantum corrections. And this is exactly where naturalness issues come in. It also goes under the name of hierarchy problem. The method to do that is to compute observables in a non-standard way, in a way which does not encounter all these intermediate corrections that we need to cancel. Of course, the method is the more technical part of the talk, but at the end, for the discussion of the talk, the spirit of this talk, the only thing you should take away from the method part is it exists. For the argument we want, the point we want to make, the only thing we need is that this method exists. I will show how it works, but if you don't like the technical stuff, you just take away it exists. So why do we do all that? I would say it makes theories more consistent, and it is very good for the intuition, because, well, for me, I always thought that these UV infinities really have physical, there's physical sense there, and now I learned that actually there's no physical sense there, because there's a method in which you can just circumvent them. So intuition is already nice, but the relevance here, as I just also pointed out just before, is that well, what are we doing in physics? We test some hypothesis. And this can be a pretty costly business, because the LHC, for example, doesn't come for free. So intuition might change the choice for a new experimental test. So that's why, in the end, it looks like innocent intuition, but there's also hard money involved, I would say. But that's what we hope to achieve. Okay, so let me review with you. So this is all textbook material. The standard way to renormalize. And I will just work. Okay, so what is the picture? There's just one slide to connect experiment and theory. At the one hand, in some experiment, for example, LHC, one measures cross sections, decay rates, and these fill the entries of the S matrix. At the other hand, all these S matrix elements can be computed because they all follow from correlation functions, from endpoint correlation functions that are computed by summing Feynman diagrams. And in the rest of the talk, this gamma with the overbar denotes renormalized physical correlation function. So if you want, the aim is to compute the right-hand side here in a finite way. So we work with, I will work just with the simplest theory possible to make our point. So this is 5-4 theory. How does it work? You need to compute its Green's functions, its correlation functions. And once you have them, you need two initial measurements at some momentum scale that you choose, some scale for the external momenta. With these, you determine the values of the parameters in your Lagrangian. And once you have them, then you are all set to make, well, predictions for any new experiment at any new external momentum scale that you want. As you wish. And of course, the red, if you want calibrating measurements, can be done at any external momentum scale. And of course, the choice for momentum scale will change the values for m and lambda, which are intermediate values. But in the end, the prediction that come out will be the same, at least, well, up to the same order in perturbation theory. So this is how 5-4 theory should work. So now, what do we need to do? We need to compute these correlation functions, these endpoint functions, so the gamma bars. At tree level, that's not so difficult because, well, there you see the propagator, which is the inverse of the 2-point function. You see a perfectly finite result, and there's the tree level contribution to the 4-point function, and that's all perfect. Of course, all these things are, all these correlation functions are expansions in the coupling lambda. So, the 2-point function begins at order lambda to the 0th power, and the 4-point function begins at order lambda. And now, this is at tree level, and now when we go to loop level, we will find the next, or all next contributions to the 2-point function and the 4-point function. So what happens when we go to loops? So we run into these UV divergences. And this is a very old observation, almost 100 years old. And so here I show you the simplest, the simplest example. So here we compute the one loop contribution to the 2-point function, and that is going to give us a quadratically divergent integral, just because, well, there's a propagator running in the loop, and that's going to give the 1 over L squared. We need to integrate it over four momentum dimensions. So we have, we have something which is quadratically divergent. What to do? First, we need to isolate these divergences. So in the process of regularization, you're not solving for them, but you're isolating them. And of course, the best way to do that is by dimensional regularization, which was invented partly in South America, partly in my country. So what's the idea here? Instead of doing the integral over 4 dimensions, I formally continue it to an integral over 4 minus 2 epsilon dimensions. Of course, this is all analytic continuation. There's nothing physical here, it seems. But what is the result here? Now, instead of doing a computation over 4 dimensions, I have this 4 minus 2 epsilon dimensions, and this is the integral I can do. So what did we achieve now? At the left-hand side, there's a divergent integral, and that we didn't know how to approach it. But now the effect of this dimensional regularization is that the divergence gets isolated, because when we go back to 4 dimensions, we take the limit epsilon going to 0. So the first contribution at the right-hand side is the divergence now, and what's left is all finite stuff. So this is a very smart way to peel off the infinity from the integral and still end up with something physically meaningful. So that's dimensional regularization. It looks like a mathematical trick. If you want, there are some lecture notes where you can find there's actually some physics in it. This is just the integral that I showed you before. If you now formally do the integral over 2 epsilon dimensions first, you end up with the integral you had before, times some factors that all go to 0 in the limit epsilon to 1, in the limit epsilon goes to 0. But the last part, the fact that epsilon is non-zero changes the last part of the integrand. So still, this goes to 1, as it should be, when epsilon goes to 0. But for every value of epsilon that you choose, you can still find some large momentum, some large value for L, that still gives something which differs from 1. So from here, this is just technical aside. This is like a physical interpretation of dimensional regularization. You see, it modifies the UV physics. So it acts like a cutoff, but it's a smart cutoff. It's a cutoff that preserves all physics. Okay, but that was just an aside. Once you have managed to isolate the divergences in these 1/epsilon poles, then comes the step of renormalization. And in renormalization, what you effectively do is you just subtract the divergences. There's many words for it, counterterms, bare quantities, physical quantities, but in the end, what you do, you just add some terms by hand in your action, and you just compute the values that you need to end up with something finite. So since we just found these divergent contributions, you need divergent counterterms. These are the delta z, delta m squared, delta lambda. And if you tune them very precisely, well, this is a formal tuning, you end up with renormalized finite correlation functions that you can use for predictions. So then there's different schemes, because you have to subtract the 1/epsilon poles, of course, but you can just decide for yourself whether you want to subtract a finite piece as well. In the MS bar scheme, you only remove 1/epsilon. In the mass dependent schemes, you organize your counterterms in such a way that at one chosen momentum scale, there are no loop corrections at all. These are just a choice. You need to subtract the 1/epsilons, and besides, you subtract what you want. That was a 2-point function. In the 4-point function, you have a logarithmic divergence, which you need to handle as well. And from then on, at least in 5-4 theory, everything is convergent, because here you see the 6-point diagram. Here you see 3 propagators. So that is 1/6 powers of the loop momentum. You integrate over 4 powers of it, so you have something manifestly convergent. And this goes up to all orders in perturbation theory. Sometimes, of course, you can have internal subdivergences when you go to higher loop order, but that can all be handled by what is known as skeleton approach. So the picture that you arrive at, this I remind you, this is a standard interpretation of renormalization. You begin with some measurements, with 2 measurements. You use your renormalized correlation functions to find the values for your parameters in the action, and from there on, you generate all the predictions that you want. So this works. If you want to take the intermediate step as a black box, it works. When you open the black box, you see there's an issue here, because actually what you did subtract the one infinity from the other. So, well, as soon as you have encountered infinities, then of course your perturbation theory expansion doesn't make any sense anymore. So physically it does work. Mathematically, of course, it's wrong from the beginning. From the moment that when you encounter the first UV divergence, everything has become meaningless. It's just, well, as Feynman said, it's a hocus pocus. It's a miracle that the correct physics still comes out. So the first aim of this talk is to see whether we can play the same game, but without any intermediate infinite cancellations. So without encountering any 1/epsilon pole in the computation of the Green's functions. So that's the first aim of the talk, to find such a finite QFT. This QFT, it will give exactly the same results for correlation functions, but its computation doesn't require any divergences that need to be removed by divergent counterterms. Okay, so here comes the part here comes the technical part, because now I just want to show you how that works. If you this is the technical part. If you don't like all the details, as I said before, the important point here is that this stuff exists. So, how does it work? As I said, we want to find a way, or not find, or at least dig out from the literature, a way to do finite renormalisation. So, a way to compute endpoint functions without running into these intermediate cancellations. So this is a problem that people have looked at for many years already. There was, so LSZ, the same Lehmann, Semantic, Zimmermann, people known from the famous LSZ formula, they had a program in which they wanted to try to compute all correlation functions without ever running into any action, any Lagrangian. That was in the 50s. There's also Nishijima in the 60s tried to continue this program, but well, we've been through a lot of literature, but it seems that this program has never come to an end. So this is still ongoing business. It looks promising, but it has not resulted in any firm result. Then there's an approach based on Kalam-Semantic equations, which was proposed by Kalam and other people in the 70s. And well, I put this one in boldface because this is the approach that you want to follow. This is the one that you want to explain, to use, and to generalize. Other approaches are by BPHZ, Bogolyubov, Parashuk, and Zimmermann. They use the so-called R operation, which is a subtraction on the integrand. So they still subtract something, but they do it before integrating. So before hitting the 1/epsilon poles, they already subtract something. So it works, but well, we are still after something better because we want to find something without any subtraction, not after integrating and not before, nor before integrating. My countryman, Nobel Prize winner Gerard het Hoofd, has a paper from 2005 where he proposes some ingenious construction, which also involves subtractions. He wants to subtract correlation function at different momenta, and with that he tries to end up with some renormalization group equation. Also, just as in the first point, this looks promising, but well, to our surprise, it seems this work has never been picked up. It's already 15 years old. I think it has 10 citations or something. It looks very promising to us, but for some reason, no one really worked on it, including Gerard het Hoofd himself. I gave a talk in Utrecht to him 2 weeks ago, and I asked him, but he said now he's after other problems now. He wants to solve quantum mechanics first before he returns to this problem. So which opens a way to us. And there's many more, and if you want, you can check our paper, and then you have a whole overview of previous attempts to do QFT without any UV divergences. So, but as I say, I put the second approach, the Kalam-Semantic approach, I put it in boldface, because that's the approach we want to follow here. So how does it work? Kalam invented this thing called theta operation. So what does a theta operation do? If you want to think about it in an algebraic way, it is just the derivative with respect to the mass parameter, with respect to the bare mass parameter. And well, if you want to think about it in a graphical way, it is just an operation which cuts one propagator in two. Of course, you know that the propagator goes as 1/L² plus m². So if you take a derivative with respect to that, you get two propagators. You get two powers of the propagator. So you can either think of it in terms of derivatives, or you can just say, every theta operation cuts the propagator in two. So on the left, you see the first loop contribution to the two-point function. When you perform one theta operation, you cut the propagator in two. So now the thing has two propagators, the loop has two propagators. And if you want, you can do another theta operation, which cuts propagators by two, one by one. Of course, the two diagrams on the right-hand side are equivalent, but I just write them like that to show you that the theta operation cuts propagators in two, one by one. So the first object on the left is just theta function, two-point function. And then we use the subject theta to show that one theta operation has been performed on it. So that's what we call gamma 2 theta. And then on the right-hand side, you see gamma 2 theta theta to show that here we perform two theta operations. So what is the sense of that? Well, that's of course that the degree of divergence of a diagram reduces by two, from every theta operation, because well, from every theta operation you get one extra propagator. The one propagator goes as 1 over L squared, so you get two more powers downstairs if you want. So any divergent diagram, if you perform enough theta operations, you will convert it into a convergent theta theta diagram. Of course, if you have any questions, I don't know how it works, because I see there's a chat, there's a
yeah, questions will be just read at the end if any, so you can just continue. No worries, Sander. Okay,
good. Of course, we can go back to any.
Wait. There is a question now that you open the can of worms. Go ahead, Nicholas.
Thanks. It's just a nice question. Is D the dimension, the one, the theta operation?
Sorry?
What
theta?
is D?
D is a derivative.
It's a derivative. Okay, sorry. I was thinking about the dimension.
Oh, sorry. No, it is meant to be the derivative with respect to the mass parameter.
I see. Thanks.
And the reason to do that is with that the derivative of 1 over L squared plus M squared is 1 over L squared plus M squared squared. So instead of one propagator, you get two propagators, which is what you want, because now you get something which is more convergent, because you get two more powers of the loop momentum downstairs. So these are the theta diagrams. And now, how does this work? Kalam derives, of course, you can go to our paper, you can go to the original work. Kalam derives two equations that we need. The first one relates gamma theta to gamma. I remind you, so gamma is still the correlation function we want to find with n external lines. And the second equation is to find relates gamma theta theta to gamma theta. And you see these equations, they contain three more parameters called beta, gamma, gamma theta. For the moment, they are undefined. We just need to determine them in the process. So these are the equations we have. Then there are the boundary conditions, which are, of course, very much like the usual renormalization conditions. So at one particular scale, you want to have only three-level theory. And here we choose that scale to be k squared equal to 0, just because it's easier to work with. Then, as an input, we need the finite three-level results I showed you already. So this is all finite. You see, there's finite boundary conditions. There's a finite three-level results. And with that, well, but that's enough to find everything. And if you want, you can even just forget about conventional QFT. You can just forget about the derivation of the two equations above. You can just take this thing as a package to compute any correlation function as a program, as a new program. So how does it work? Here I take the first equation for n equal to 4. So here we are trying to compute the 4-point function. To be precise, the first loop correction. So that is the second one, the first one on the right-hand side. That is the diagram that normally is UV divergent. Now we try to compute it in a new way. As you see, at the left-hand side, we have something which is finite. It contains three propagators. At the far right-hand side, there is the three-level input, which is also finite. So as you see, the only divergent quantity we have here is the one we're after. It's the first one at the left-hand side, at the right-hand side. It's the standard one loop correction to the 4-point function. So what can we do now? I showed you before, just 2 slides ago, I showed you we have the equations and we have the boundary conditions we can use. So if you impose the boundary conditions, you get a condition on beta and lambda. The left-hand side is still completely finite, completely defined. So the result of this first exercise is that you get a differential equation for the quantity you're after. And you have one condition already on beta and gamma. And this is all finite. But this was the computation of the 4-point function. Now we need to compute the other divergent guy, which is the 2-point function. And again, we take the simplest thing, we take the one loop correction to the 2-point function. This is the diagram I showed you in the very beginning. So at the right-hand side, you see the diagram that we want to compute. It is quadratically divergent, as I showed you already. So we need 2 steps here. At the very left-hand side, we have the object gamma 2 theta theta, which again has 3 propagators. So this is completely finite. Then I use the second equation that I had. I showed you there are 2 equations here that converts the gamma theta theta into gamma theta. That's one step. But this thing is still logarithmically divergent. It has 2 propagators. And then you use the first equation to compute the one that you're actually after, the 2-point function. So here you need to use both equations. And well, there's no need to go into details. But you get 2 equations, which in the end help you to find the thing that you are after, the diagram at the very right-hand side. And in the process, you also find 2 conditions on gamma and gamma theta. So in the end, you end up with a computation, this computation gives you the one loop correction to the 2-point function, the 1-point correction to the 4-point function, one loop correction to the 4-point function. These are the 2 objects that normally involve UV infinities, but now we haven't encountered them. And in the just in the process, we found these objects beta, gamma, and gamma theta. And the nice thing about this approach is that it works recursively, because now you have enough material to go to the next step. Now you can compute 2 loop diagrams. And from there, from these results, you can compute 3 loop diagrams. So order by order, of course, it becomes very complicated. But this approach, this Coulomb-semantic approach, helps you to find correlation functions up to any order without ever running into any infinity. Well, that's very nice. Then you can generalize it. You can compute cosmological constant without any extra correction. You can compute the effective potential without any intermediate cancellation. You can show that the wave of the Higgs field doesn't shift from heavy new physics. This is a problem that's very, this is an urgent problem in theories of grand unification, where the problem is always that the Higgs vacuum gets shifted by a large amount from the existence of some high UV completion theory. All to say, this helps you to eliminate any UV infinity from your computation. So that was from now we are at the point where I showed you how any UV infinity can be circumvented. But in the end, we are not. I think this is more or less known that infinities are formal. But now we go to the more practical part. Now I don't want to look at infinities. I want to look at these large loop corrections. And for this, we need the simple setting is a model of 2 fields. 2 fields with a large hierarchy in between the masses. So there's small phi, which is a light field. Its mass is given by small m. Then there's capital phi, which is the heavy field. Its mass is given by capital M. And we assume large m to be much smaller. Capital M is much larger than small m. And then, of course, there are the 3 couplings allowed by the symbolism theory. So what happens? Now, if you want to compute a 2-point function of the light field, I call it gamma 2, 0, just to indicate that I have 2 light fields and 0 heavy fields. This is exactly the thing that we're after. This is the thing that I showed you in the very beginning. This is the problem where the two-point function gets a loop correction from the light field running in a loop, which is fine, but there's also a heavy field running in the loop. And after renormalization, so after you already get rid of the infinities, you are left with this renormalized two-point function that you see in the bottom, which has a three-level contribution. And then there's one loop contribution from the light field, which is proportional to small m squared, which is still fine. And now but the heavy field, the loop with the heavy field running into it, gives a contribution which is proportional to large m squared, capital M squared. So this is what I showed you in the very beginning. Here you see that new physics. In the beginning, I just called it by lambda. Now there's a more there's a more detailed prescription of this new physics. Now you see how this heavy physics, how this heavy field has a large influence on the two-point function of the light field. So this is exactly the thing that people are worried about. Here you see how if you want the Higgs field, gets very large mass corrections induced by some heavy field living in a high energy UV completion of your theory. So it's exactly the presence of this capital M squared that is the root of the problem. Because, okay, what happens now? If you want to compute the mass of the light field, you find, as I just showed you, you find this very large quantum correction, these very large loop corrections to that mass. So you need an order m squared or a large m squared cancellation between tree level and loop level to explain the low value that you measure. So again, if you think of the intermediate steps as just some black box, it all works. You take some measurements. Okay, now you need 5 because there are 5 couplings in this theory, 2 masses and 3 couplings. You take your initial measurements, and at the end of the day, you'll get your predictions for all new experiments. So with a black box, if you view the process as some black box process, it all works. But if you open the black box, you see that to get to your predictions, there was a very large cancellation. There was, if you want, a very large fine-tuning, because there are two numbers here of order capital M squared that result in an observed value of order small m squared. And that's exactly what people call hierarchy problem. Because as I've shown you, to end up with this, if you think about this heavy field phi as a field which occurs in grand unification, so it is order mass order of 10 to the 16. So then you see that to find the Higgs mass of order 100 GeV, to find that actually you need a cancellation of, you need 2 numbers of order 10 to the 16. You need them to conspire in such a way that you get your result of 10 to the 2. So it's like order 10 to the 14 cancellation. That's what people call the hierarchy problem. Is the problem? Yes, people say, because even if they occur at the intermediate stage of the computation, such a cancellation is unnatural. And from there, as I showed you in the very beginning, that motivates searches for new TeV physics. Because if new physics comes in at a lower scale, you need the cancellation that you need are much smaller. So if you want much more natural, and that has been one of the main motivations for all these low energy supersymmetry models and all the others that you see here. So this is how hierarchy problem, how naturalness is really a hot topic in our field. In this cartoon, you see the number of papers which have hierarchy problem or fine-tuning or naturalness in their title as a function of year. This is just to convince you that this is really an urgent problem. Even, okay, it's a formal problem, but it's still it is something that attracts a lot of attention. So we hope if at one point everyone will accept our paper, that this graph will go to 0 soon, and no one will talk about naturalness anymore. But I will come to that. There's other people that say, well, there's no problem at all, because in the end, the cancellations are in between unphysical parameters. These are just parameters that occur in your action, but they don't have any, there is no way to measure them. It's all formalism. So even if there's large cancellation, well, why worry about it? Other people say, why is 10 to the 14 unnatural if you don't have a measure on these numbers? Okay, people say we like numbers of order 1, but well, that's us. That's not, well, that's just us describing nature. And there's a more like intermediate point of view that says, well, you can still talk about natural, unnatural, even if you don't know so well how to interpret these numbers. So the whole aim of our talk is that we stand with the no. We are in the no camp. We want to convince you that the answer here is no. And to do so, what I'm doing in this talk is to show you formalism, which doesn't run into these corrections at all, into these cancellations at all. So if you see that there's no fine-tuning around formalism, then you understand that fine-tuning is really formalism dependent. The whole naturalness concept is formalism dependent. So as I say, all our talk is to give you new evidence why you should choose no at this point. And to do that, this Kalan-Szymanczyk approach that I just showed you, it was written in the 70s in the context of one field. So just the 5-4 theory I just showed you. Of course, if we want to address this problem, we have a theory of two fields in its very simple setup, a light field and a heavy field. So now there's really no reason to go into details, but now, okay, there's two masses in the field. So there's two kinds of theta operations. Everything becomes more complicated. We devote an entire new paper to show how it works. So this is our, if you want, this is new work. We just generalize this method to two fields. And well, here you see the first equation, it becomes very large, and the second equation is really hopeless. But again, the thing to take away from this part is that yes, it can be done. This Kalan-Szymanczyk approach can be generalized in a way in which even in the two-field models, you can compute any correlation function without any divergence or without any large cancellation in the middle. And I show you quickly how it works. I'm interested in loop corrections to the two-point function of two light fields. With this condition, it begins at order lambda squared. So the first corrections come from this sunset diagram that you see here. So we have light external fields because we are computing the correlation function of light fields. And there's a heavy loop running through it. And well, this is a large computation, but if you want, this will be gamma 2 then. You can compute, you can convert them into gamma 2 theta thetas. So these are at the left, at the downstairs, you see 4 diagrams that are hard to compute, but for sure they will all be finite. And then you can use the boundary conditions, you can use the equation I just showed you to compute the contribution from this very first diagram that you see in the middle in a finite way. So here in this result, C1 and C2 stand for complicated but finite expressions involving Feynman parameters and all. So you get the result that you always get, because in this result you get the result that you always get, but without having made any subtraction. And you see this is what you want, because if you expand it into the region of low momenta, low external momenta that you're interested in, you see that this one is actually small, plus, well, it is the standard result, plus contribution from heavy physics, but these are all suppressed by powers of the large mass. So you get the result that you always get, but now without having imposed any condition, without having subtracted any large number, which is exactly what we were after. So to conclude, to put everything in context, what have we done? We have looked at standard lambda 5-4 theory, but now we computed its correlation functions in a way in which we never found any intermediate UV divergence. To do that, we use this finite Kalan-Szymanczyk method, which gives you the package, which gives you the equations, the boundary conditions to compute all correlation functions all correlation functions you're interested in. If you want, you can even take these Coulomb-Semantic equations and these boundary conditions as a new formulation of Q of t. So then you say, well, you just forget about this loop about these divergent diagrams. You just say they don't, in my new formalism, they don't exist. What I have are the equations and the boundary conditions. And from there I compute everything. Now, what we did, the technical work that is behind this talk and behind our papers, is the generalization of this method to the two-field case, which is a nightmare, but again, what we need for this talk is the fact that it exists. And with that formalism, one is able to compute the light field two-point function, or if you want, the Higgs mass, without having to subtract any large or the large m squared mass at any point. And these subtractions, these cancellations, are exactly the root of the hierarchy problem, of all naturalness problems. So with this, we show that all these cancellations, all these naturalness thoughts, are actually all formalism dependent, just because we just found a formalism in which they don't occur. And that should strengthen intuition. That's our motivation to state that there's really no physical content in hierarchy problems, in naturalness problems. And in particular, they should not be taken as guiding lines for the design of new experiments, or for deciding which new hypothesis to test. Remarks. Yeah, I put don't write this at home, because you see that for any loop diagram, what I want to say is that any diagram, to compute it in this way, you need to compute many new diagrams and then integrate them back. Of course, if you just need for practical purposes, if you need some correlation function, of course you just take the usual way, usual divergent way, subtract divergences, and done. So all we're doing here is more. It's a matter of principle. If you want to, you should not use this formalism for real computations, because it's very complicated. It's needlessly complicated, unless you want to make a point of principle. Another important point is that we have not explained why the Higgs mass is so much smaller as the scale of new physics, for example, the Planck mass, or we don't give any explanations for why the cosmological constant is so much smaller than Planck mass of the fourth. So yeah, we are not explaining why this hierarchy exists, but we are dealing with the consequences of this hierarchy. We are showing why low energy physics is still stable against these huge quantum corrections. With that, we argue that, of course, new TeV physics it's of course possible, but it's not necessary. It would not solve any naturalness problems, because these don't exist. At the technical side, it would be interesting to think about gauge fields, because gauge fields, well, then you have massless fields, and it's not clear how this method would work for massless fields. I'm sure that it has to work, but this is something that should still. The question is still how to generalize this Coulomb-Semantic formalism in such a way that it can also deal with massless fields. Another thing is that it should be possible to write the same method based on MS bar formalism. I mentioned the paper by Gerard het Hoofd, which I think with this in mind, it should be possible to work that out further and see whether we get the same results. And the very last point, so far I only talked about phi-4 theory, which is renormalizable. But in principle, this theta operation, you can do as many operations as you want. So even if you have a diagram with degree of divergence 14, if you do 8 theta operations, in principle, you can scale it back to a convergent diagram and then work your way back up. So in principle, this should also be able to address non-renormalizable theories like phi-6 as the easiest example. And of course, the very last statement is that your comments and questions or emails are very welcome, because well, there's still a large ongoing debate on whether how there's a large debate on whether this is all useless or very interesting and very meaningful. And we are at the second line, but we encounter people that take more the first point of view. So with that, that's all I want to say. So yeah, I'm curious for questions.
Thank you, Sander, for this very interesting talk. Let me see. Yeah, there are a few questions, so we can start with the first one that appeared on YouTube. It is related to your first two slides explaining the CS method. So the person is asking in the last equation, what's
where are we?
I think where there was gamma. The question is like, why do you have gamma and now gamma bar, and if there should be any difference?
I think when you introduce the color semantics, yeah.
Okay, let me see. So I think in the beginning I was talking about renormalized. It is a very good point. In the beginning, I was telling you that I was interested in what I call gamma bar, which are renormalized endpoint functions, right? And in this Kalan semantic method, I think I did not write the bars. Where are we? This would be here. Oh, all the bars are here. So what is the question?
Yeah, we can, okay. Let's see, there's a little bit of delay, Sander, so we can ask this person might.
Well, but so what I want to say, the idea of this method is that everything is renormalized from the very beginning, because this method doesn't need and doesn't require any regularization or renormalization. Once you have these equations, these are renormalized endpoint functions from the very beginning. So yes, every capital gamma you see here should have a bar. And if I forgot one,
can you go one slide back? Yeah. Okay.
This one.
I guess so. Yeah, I think
that is a very, very good point.
Okay.
Because so Kalan wrote this method. Kalan has derived these equations, which are all in terms of renormalized quantities. But to do so, he actually began from an equation in terms of bare quantities. Then he converts left-hand side and right-hand side into renormalized quantities. So he ends up with something that is completely, that only involves renormalized quantities. So the answer to the question is that to derive these formulas, you begin from bare quantities. But what we argue is, well, we're not really interested in the derivation. We just begin from here. We just want to begin from this package. And then we only have renormalized endpoint functions. So yeah, I think that's a very good question.
Okay, thank you. There is another question over YouTube. It says, but I think you addressed it at the end of the talk, but maybe you might want to comment a little bit, is how do you do renormalization? It seems you can do this even for non-renormalizable theory. Can you comment? But I think that was your last remark, right?
At the very end, the question is how you would do it for non-renormalizable theories.
Yes.
Oh,
and if you can comment, yeah.
Well, I think, look, people always say that non-renormalizable theories are non-renormalizable. That's why they're called like that. But the precise statement is that you can still compute any endpoint function, but up to any finite order. If you're interested into the 6-point function up to order lambda cube, you're still able to do it. So I think you're going to find some equivalent statement to that. But yes, I think this of course it's not that now no, but it's exactly in that sense. I think it can be done. And you will arrive at the statement you'll also find in the Weinberg book. At one point, Weinberg writes, actually, non-renormalizable theories are as renormalizable as the renormalizable ones. I think you will end up with that statement.
Okay, thank you. I think we have here some questions in the coordinators. Then also people on YouTube is saying many thanks for your clear and nice talk. Congratulations on your work. I think Joel has a question, then Nicolas.
Yeah, I was. Can you go back to your
let me see. The first ones when we did it for
Yeah,
the
first
field.
part. Yes, right. Yeah, no, that where you were, and the next one, and the next two couple of slides. Yeah, that. Okay, great. So here, since you're using, you have finite quantities here, right? So
Sorry.
I mean, you have finite quantities here.
Yes.
So the point would be, okay, now I need to integrate the derivative of gamma bar over M, right, to get my finite correlation function.
Yes.
So okay, so first just to get out of the way something that's bugging me. So what are the integration limits there? They're defined by the boundary conditions.
Exactly. All integration limits are set by the boundary conditions.
So then this M this M on the second one is an M hat or something, right? So it's a different.
Sorry.
The second one is an M hat, right? That's correct, right? It's like
yes. But everywhere, because once you're here, everything is normalized from the very beginning. So it's M hat, it's lambda hat, as you wish.
So that in that case, of course, you will not be getting any divergences here by construction.
Exactly.
Right. That's the whole point. Because I was concerned about the possibility of getting a divergence after integrating over M, right? But of course, you're not gonna get that because it is by construction that everything is coming out from finite quantities. Okay, that does make sense. Okay, so I'm gonna leave Nicolas for a while while I think about my other question because I wanted to get this clear. Okay, so thanks for that, and I'll be back.
Okay.
I'll be back.
Thank you, Nicolas.
No, but just to be very clear, so this formalism was not invented by us. So what we do is at the technical side we generalize it to the case of two fields, and at the physical side, we are using it to make points about naturalness, about absence of mind.
Sure. That's what I need to think about right now. but yeah. I just wanted to be sure about this part.
Thank you, Nico.
Okay, thank you very much, Sander. Very nice talk. So you were talking about naturalness. So I'm not sure if I got your point exactly. So you're saying that, for instance, this theory is not natural, but at least you can guarantee that it's technically natural, right?
No, well, technically natural for me is something else. Technically natural means that when some parameter is when some parameter is small, that is still technically natural if in the limit when it goes to 0, there's a symmetry being restored. But I mean the whole picture that we want to challenge is this very idea that if I have a large mass is okay. I'm trying to compute this diagram. So here I'm interested into the mass or the 2-point function of a light field. Then there's a heavy field running in a loop. This is going to give a very large answer, which means that I need to cook up a very large counter term without to explain why the Higgs mass, for example, is as small as this. So the idea of our method is that there is a new way to compute this one, where it is not proportional to this large scale, which means that I don't even need any renormalization. I don't need any counter term to cancel them. So basically, both numbers of order lambda squared don't occur in this method. So there is no cancellation between two numbers because both numbers are absent.
Okay, so maybe I got confused at the very end. You say that for instance, you had no explanation why the Higgs mass is much smaller than a Planck mass.
Yeah.
Constant.
Yeah. That's a very good point. Look, of course, the fact is still that there is a heavy field running here, and the heavy field is, as its name suggests, the heavy field is heavy, the light field is light, and this is something we see. Well, we have the light Higgs field, if there is rank unification, for example, they're very heavy scalars. So what we're doing here, we are computing the effect of the existence of this heavy physics on low energy physics. But to explain why such a heavy field would exist in the first place, I don't know. That's what I'm trying to say here. All we're doing is dealing with the consequences for loop contributions of low energy physics, the consequences of the existence of high energy physics, of like new extreme UV physics. But if you ask why is the Higgs mass so much smaller than the Planck mass, we don't know. All we're saying is that that does not have any consequences about naturalness or fine-tuning or anything. But well, the cosmological constant problem, for example, is why is the cosmological constant so much smaller than the Planck scale? Well, I don't know.
Yeah, exactly. But I mean, if we agree with that, cosmological constant is much smaller, we don't have to care. I mean, the question why such big difference exists. I mean, we understand why it is stable, because I mean, these corrections will not try to raise the cosmological constant. Okay,
so the aim of this talk is indeed to show you. Okay, look, in the standard method, the existence of heavy physics is going to give heavy contributions, large contributions to your correlation functions, which means that you need to make large subtractions. You need to subtract another large number to end up with a small number that you observe. In this method, even if this heavy physics exists, it never gives any large contribution to correlation functions.
Yeah. Okay. Thanks.
You're welcome.
Thank you, Sander. There's another question I just copied here in the Zoom. It's a little bit long, so let me say it. It says like, can we imagine this finite renormalization scheme to essentially derive a mapping between the IR value of a parameter and the UV value of the parameter? Know that two close potential values of the parameter at IR becomes very highly separated at UV. Is this a problem?
Yeah, I would argue that that is still a manifestation of the first problem. That is look, what we're doing is we are computing correlation functions in a new way, right? But in the end, if you ask questions about the running from low scale to high scale, that still involves the same renormalized correlation functions. So no, we're not doing that. But in the end, I would say that is all these running issues. In the end, also okay. Look, let me put it in the right way. When people worry about running, about light fields becoming heavy in the UV, the underlying question is always, how can I generate a light scale out of heavy physics? But for us, that is a question about the generation of this scale, so about the generation of the high UV. So that is exactly this question again. All we are dealing with are the consequences, not the generation of the two scales.
Okay, thank
so
you.
I have a follow up. Could you go to your, I don't know which one it was, then can you go back a couple slides, like 3 slides maybe? Yes, right there. So this is the issue, right? This is the point that bothers everybody, right? That the fact that the loop corrections will be proportional to the heavy masses, right? Which is what you're having on the first line, right? Which proportional to the heavy.
But watch out. This one is already in the region where I'm interested in.
Sure. Exactly. I know. So the point here is that you're getting your correction, which is proportional to m squared, to big M squared, and then you set your boundary conditions, and you say, okay, my boundary conditions determine that when k is very small, I need to have the correct mass.
This
right?
one.
The mass that I observe. Yeah, which is a little m, right?
Yes.
So that is what drives you to use a very small k.
Yes, but in general, I mean, when I'm measuring the Higgs mass in some experiment, I only have access to small values of the external momenta.
Sure. But the point is that that comes from your I mean, because when you're measuring the Higgs mass, right, you're using no, give me a second. Let me rephrase that. So when you set your boundary conditions, you say, okay, I want that my propagator will give me the Higgs mass when k is around some value, right? So I will get a pole in the propagator when k equals, right? So there we are saying, okay, I want my masses to be small. I want my pole in the propagator to be at small values of k.
Yes.
Right.
Yes.
So that's how you are.
Yes.
Sorry, because I'm thinking about this while I speak, right? So I'm going very slowly. Right. So the point is that, right, that you are putting this on your prescription, that you want your mass to be small for small k.
Yes.
Right. Which is what you also do in your standard case where the divergences come out, and since in the standard case it's uglier than your method, which is much more elegant because it uses always finite things and the things that you observe experimentally. Of course, here we will not be seeing these cancellations, because your requisites are everything must be finite and everything must be the way I want them to be, which means small mass at small k.
Yes.
Right?
Yes, but in the standard approach to renormalization, well, at least because now this is all equivalent to the mass-dependent schemes. So as you say, you impose that at one value for external momenta, the renormalization scale, at that scale, you want to have zero quantum corrections, right?
Yeah.
And so that is so. Of course, what we're doing here. Well, what you see here, this is of course very similar to that one. I mean, this is exactly that condition.
Yes.
So if you want, here you're putting in the same renormalization conditions. Here we call them boundary conditions because there is no renormalization going on. So of course, in the end, if you get the same input here, so you will also get the same output, because what you find here is exactly what you want. But the point is that if you do it in the standard way, you will have to make a large subtraction to get it. And here you find the same result without any subtraction. That's the difference.
Yes. Yeah, my point is that in the standard approach, you're subtracting non-physical things in a way, right?
Yes.
Well, in your approach, you don't have those things, right? They're all of them are physical, right?
No, I'm still not. I mean, in the end, lambda and m are still parameters that appear in my Lagrangian. I would always say,
yes, okay,
I would always have this picture. All parameters that appear in your action are always Lagrangian parameters, and they're only tools. The only thing they do is, only thing you want is you do some first measurements. So if you have 5 parameters in your action, you do 5 measurements. Then you put it into your Green's function. It doesn't matter how you found them, and from there you find predictions. So parameters in the Lagrangian are always unphysical. That's why you should never worry about cancellations between them. Which is exactly our point.
Yeah, which is a point on the first.
So but so the only what we do with this method is that we are just giving more meat to this statement. But I would say that even in the renormalized Green's functions, it doesn't matter how you found them, even there, these parameters are still unphysical because it just their value depends on your choice for initial experiments. The only thing which is physical, and is still within perturbation theory, is the conversion from initial experiments to resulting predictions. That's the only physical thing there is in all of this business.
Okay. Okay. No, it's very, very interesting what you're
Thank
doing.
you.
It's made me think. Think a lot.
But you know, we get the one rejection from the after the other from JHAC referees. So
Oh no.
people all say it's trivial or it doesn't solve the problem. So which in a way is also encouraging. But yes. So thank you.
Okay, thank you very much. I think we're past the hour, so if you have more questions, you might find Sander's information on Low Physics WordPress or whatever, and you can continue this discussion. Thank you, Sander, for sharing your work. This is very interesting work. And for all our audience, remember we have another webinar next week. It's going to be about straight masturation spirals with the future LISA instrument. So thank you very much, and let's stay and keep tuned. Thank you very much. Bye.
Bye. Okay, that was nice. Thanks. Thanks a lot.
Okay. Yeah. Cool. Thank you.